Okay. So this week I will first say about is simultaneously diagonalizable, and then I will introduce the bracket notation and tensor products, then talk about some of the pure state and density matrix. Okay. So let me just do the final theorem about linear algebra, right? So this is a theorem. Oh, this is bad. Okay. So let's see. So let's take a field to be a complex number. Oh, this is so bad. And let's say V is some finite dimensional vector space of this F. Let's say dimension V is less than infinite. And there is a theorem says that if T and U, these are metrics, are normal, and if there are the commutes, this implies that this T and U are so-called simultaneously diagonalizable. So it's diagonalizable. Okay, so remember that no. So let me just record the definition of normal means that T star and T star T are the same. So as we shows that before that since T is normal, so there exists also normal basis, right? That such that T is diagonal. But this theorem says that if T and U are both normal and they are commutes, then they are basically simultaneously diagonalizable. Basically means that you can find a basis of V such that T and U are both diagonal. So in quantum mechanics, right? I believe that you guys done some basic quantum mechanics that you know that if TU the special case are TU are Hermitian. So Hermitian means that these are the same. Then there are simultaneous. Then they are simultaneously diagonalizable. And so this is the theorem. And I don't know where you guys see any like rigorous proof on this theorem because in quantum mechanics book that people just tell you, oh, this is true. Okay. So I will like quickly give the somehow like more rigorous proof. So is anyone like have question about the statement? So let me just talk about the proof. So the idea is that say quickly proof. So the proof is that so we just take W to be some E lambda. So E is the eigen, so it's the eigenspace with eigenvalue lambda of T. And so we know that this W is called a T invariant. So T invariant means that for every X in W as a vector, this T of X is also in W. It is trivial because X is an eigenvalue of, as X corresponding to eigenvalue, as X is eigenvector of T, right? So T of X will just be lambda X. Okay, so obviously that for all X in W, basically it's E lambda, then T of X will proportional to X. And remember that T is normal. So as a proof that T is normal, so this any eigenvector of E lambda will corresponding to eigenvalue will become the same eigenvector, but with corresponding eigenvalue lambda star. So W is also T star invariant. So T invariant, T star invariant. And for the lambda bar, right? So for the complex conjugate. And notice that so notice also T star is normal, right? T is normal. So there's a theorem that says that okay, I will explain this theorem after. But you can believe me that there exists a polynomial G. So there's some polynomial G such that this such that T star can be written as polynomial GT. So basically this means that basically this T star can be written as some AN T and AN minus 1 T n minus 1 up to A0. Okay, so T I can represent T star in terms of T. So once this is true, then you immediately show that let's say U star T is also TU star. So this means that U star TX for any X is the same as T U star X. And this is like proportional to X, right? So this means that this U star X is also belongs to E dot, right? By just changing it. So that means that this means that this E lambda is also U star invariant. Right? So this means that E lambda is U star invariant. And similarly, the same reason will show that E lambda is also U invariant. Okay, so what I'm saying is that this E lambda is both like T invariant and a T star invariant and the U invariant and the U star invariant. Okay, so that means that okay, so this is the first thing. And the second thing is that this is a simple fact that when W is a subset of V, if W is a T invariant subspace, then obviously that W per the all the orthogonal vector along that of W will be T star invariant. So what I'm saying is that this TU equals to UT condition, if you restricted everything in terms of W, will be trivial. Will be the trivial thing. But if you restrict to W per, it also be trivial thing. So let's write this TW and this is UW. So what I'm saying is that this TW is normal and this UW is also normal. And this TW per is also normal. And this UW per is also normal. And they satisfy this TW, U restricted W is the same as UTWW. And the same for the per one. So what I'm saying is that if I take the subspace and I do this kind of decomposition, then all the normal condition will be true in the subspace. So basically, by the induction that we finish the proof, because I already know that this is true. This statement is true when dimension is one, right? Because in dimension is one, these are all scalar, so these are simultaneously realizable. But now I take a subspace and do a restriction that this is true. Okay, so this is somehow like the final review of the linear algebra. So yeah, so we can forget about all the difficult thing and go to the standard like review of the introduction to the quantum mechanics. So yes, yeah, so this once we review this quantum mechanics, then in the following week, basically next week, we will talk about some interesting stuff. Okay, so I will try to like review quantum mechanics. So I believe that is anyone the first time learned about quantum mechanics, or you don't know anything about quantum mechanics? Everyone knows about basic quantum mechanics, right? Okay. So there are very different approach to quantum mechanics. So in quantum information, there's a very quick one that we just tell you some axiom, and you just believe this axiom is true, then you can do you can just do the quantum mechanics. Then you will feel like very strange why like you take like 1 semester or 2 semesters just try to learn the quantum mechanics. Because they are trying to teach you that this Schrodinger equation and tell you how to like compute the amplitude between the one wave function to another. But in quantum information that we can just do the discrete one. So for discrete quantum mechanics that basically is just linear algebra. So I will use so if you go to the textbook that we will use some some like very similar to what mathematics did is that we just tell you some axiom and then you just believe this axiom and you believe this is quantum mechanics. And there will be like three axioms. So in quantum mechanics that we will talk about so-called states. And then we will talk about so-called evolution, basically so-called unitary evolution. And the third one is so-called measurement. Oh, this is so bad to write. And okay. So these are like somehow like axiom, and you are not you can try to like think why these are all true, but yeah, it's fine. Okay. So let me just quickly say about this state. I mean, this is similar as like any kind of physics course, right? If you in general physics or electrodynamics that people tell you that oh Maxwell equation is true, and this Schrodinger equation is true, and whatever equation is true, then you just believe it, and then we believe this is true, and then you will give some derivation and give some experimental phenomenon, and you just check this experimental phenomenon is the same as the real world. If it is, then you try to convince you guys that you just convince yourself that this theorem is true. This equation is still true. So for quantum mechanics, it's the same that these are axiom that you are not you cannot you cannot try to derive this axiom by yourself or other kind. But there's a mystery one about this measurement. So I will try to like explain more about this. Right, so basically what the first one is states, right? So state is simple, state just in quantum mechanics that we will talk about so we will first of all so-called pure state. So pure state is simple, just some vector in the complex vector space with complex coefficient. Okay, so simply speaking, the state just z1 up to zn, and each zi is complex. So this is just a vector. Okay, but so this is the column vector, right? So is it? Yes, column vector. So in quantum mechanics that there's a bracket notation. So we will write psi. So this is a bracket notation. This is called cat. So usually we will write cat as a vector. Okay. And there's another one called bra vector. Just you can imagine that someone just once you write this, then you can imagine that basically it's just this complex, just a complex conjugate of this. Okay. So this is just notation, and we can do inner products. So as you know, that inner product of this guy and this guy will just be this inner product with this and this, right? So you can do it as a matrix multiplication. So let me just write clearly. So if psi is a1 up to an, and then this phi is basically, let me just write. So if phi is just b1 up to bn, then what's this inner product? Just take b1 star a1 plus b2 star a2 plus bn star a. So you can just do this as a matrix multiplication. You just imagine however I write phi as this, then phi the complex conjugate will just be row vector, and then you just do the matrix multiplication of this vector and this vector, then you will get inner products. Simple enough. Any question? Okay. So this is just this. And then we can also as a linear algebra, right? We can talk about so we have the linear operator as before, and also you can define normal and do the same thing, right? Okay, so the only non-trivial part in this kind of notation is basically so-called tensor products. Is anyone that you did this? Okay, so if this is the first time you heard about tensor product, you can tell me. Is anyone that this is the first time you know about these tensor products? Okay, so tensor product is that I give you two vector space V and W. Then there exists another vector space called V tensor W. And if you come from math department, there's a thing called a universal property to define, but it's very abstract, somehow abstract. So I will not use this definition. I will just tell you how to like do this matrix tensor products without going to so-called universal property. So simply speaking, that if this V is dimension m, and the W is dimension n, then this is basically a vector space. This guy is a vector space. Let's say with dimension just m times n. And so we will use so all the elements. So let me just write down, right? So all the element belongs to this V tensor W. Just be written as linear, just the linear sum. So just some linear combination of any vector Vi in V and the Wi in W. So it's Wj. So I can write as Aij on this. Okay. And so this is basically a definition. Up to some technical detail. But okay. So let me just all element inside this is basically written as a linear combination of this Vi and Wj. So we will choose. So usually we will choose this Vi to be also normal basis. So this Vi is also normal basis of V, and the Wj is also normal basis of W. And you just take all this notation and take the sum as so this is all the element inside. And sometimes that people will like be very lazy, right? So sometimes that you will see someone write this, or someone write this, or someone write this. So these are basically the same thing. So for example, this is so let me just write this as simple example. So the simple simple object in the like quantum computing is called a qubit. So qubit just basically is just two-dimensional vector space. So just some complex. And so there are two bases, right? So people will just use very simple. So people will just use 0 as the first basis and 1 as the second basis. And if you are not if you think this is weird, then you can imagine, then you can just think by yourself, this 0 is just 1, 0 vector, and 1 will just be 0, 1 vector. So all the element in V, then I will write A0 plus B1. And I will call this is psi. So if you think this is weird, then you can just in your mind think this is just a B vector, as this. Okay, and what is the element inside V tensor V? So for example, there's an element that remember this all the element inside V tensor V is basically written as you take some vector in V and another vector in this is also V, and you take the you take this sum. So for example, there's an element that's called 0, 0 plus 1, 1, right? This is a state inside V, inside V tensor V, right? By definition. And this is famous one called Bell state. And we will spend like a week, okay, probably like 2 weeks, just prove some basic, some very, very non-trivial property for this state. Any question? If you have any question that, yeah, hopefully you need to ask. Okay. So yeah, this is a tensor product. And I also need to tell you some property, these tensor products, right? So if you have this kind of thing, if you take a multiplication of Z, then we'll identify, actually, it's identified with this ZV, right? Remember, V is a vector space, right? Element in the vector space. So this Z, their multiplication of Z can apply on V. So we will identify with this tensor ZW. So I write equal, right? But mathematically, you can it should be identified. So I can. So this is the property. And then if I have V1 plus V2 tensor W, then I should use V1 tensor W. It should be the same as this. And also the same for the third element. The second, like it's also linear in the second component. So it's V tensor W plus W2 that you get V tensor W1 plus V tensor W2. Oh, these are just common property. And if you take all some A and B be the linear transformation, let's say A is a linear transformation from V to V, and the B is a linear transformation to WW, then by linearity, that if I use a tensor B, okay, so this is another notation. So remember that I only defined I previously, right, I just defined two vector space tensor products. But now if I take two linear operator from V to V and B from W to W, then I can define the A tensor B as a large operation act on the V tensor W. But I just define it as as the A great notation. Let me just write. It's a this is V tensor W. Then I can define it to be a V tensor BW. Simple enough. Okay, so basically this is the property, and we can so remember that I review a linear algebra for a week just to tell you that the so-called inner product space, right? So we can also define the inner product between of this tensor product. So remember that the inner product is that I give you I give you element in the U and V, U in V in V, capital V, and this will give you complex number, right? This is the inner product. But I can also define inner products. I can define inner products on the V tensor W. So there is a natural inner products on V tensor W. So why because let's say I take one element inside this, so I can write the AI VI tensor W. Let's say WI. Suppose it's true. Suppose this is the element inside V. Inside V tensor W. Now I can take another one. Let's say I take this Vj prime Wj prime. So this is then I can define the inner product. Suppose I have two inner products. One is on W, one is on V, one is on W. Then the natural thing is that I just define it to be like I and J and AI star Bj. So this is our coefficient, and I take this inner product with this and this inner product with this. So I can write as Vi Vj prime Wi Wij prime. So yeah, so basically it's just some computational convention, but yeah, simple definition. Is it okay? So remember that we already say what this means, right? You just write Vi as a standard basis and Vj is a standard basis, and W also, so we can compute the inner product as we just said. So remember that for example, if I write phi to be A1 up to AN and the psi to be B1 up to Bn, then the inner product with this phi and psi will just be summation AI star Bi from 1 to N. So this is well defined, this is well defined, and this is well defined. Okay. Good? Good. Very simple. Okay. And is it uh is it okay? Okay, okay. Is it good? Okay. So let me Okay, so these are tensor products. Another thing I need to talk about called outer products. So what outer products that you can take, let's see. Right, so you can take any vector v, and write as this. So this is called outer product. You can also write let's say v1. Let me just use v. You can write this is called outer products. So what this means? So this means that for example, if I so remember that whenever you have some confusion about this bracket notation, you just go back to your standard linear algebra. So let's say v. Let's say I write v as v1, sorry, a1 up to an, and then this cat. This is called bra. This is called cat. This is called bra. So this is so bracket notation was invented by Dirac. Okay. So this v will be just this a1 star, a2 star, an star, and then you just go back to if you have this in mind, then computing this just as a matrix, right? You just write this v as a1 up to an, and the a1 star up to an star. So your linear algebra, right? This is n times 1 matrix, n times 1 matrix. This is 1 times n matrices. So the results will be n times n matrices, right? So this will be n times n matrices as a1, a1 star, a1, a2 star, a1, an star. Good. And a2, a1 star, a2, a2 star, a2, an star, an, a1 star. And then finally go to an star. Good, good. And notice that this is called inner product, right? This is different, right? This is start from the cat. This is bra, and this is called bread and cat. So this is bracket. Okay. So for this one, which is inner product, right? So it's different. So you do this and do this. So this is just stupid comparison, but just tell you that how to like understand this bracket notation. So it will be just so this is 1 times n matrices. This is n times 1 matrices. So the result will be 1 times 1 matrices. So which is a scalar. That's the summation of ai absolute value and I from 1 to n. So this is called outer product. This is the inner products. Good. Good. Okay. And okay. So let's maybe do a simple example. So everyone knows about Pauli matrices, right? If you don't know about Pauli matrices, that's fine, that I can tell you. So there are 3 matrices which is so common that which is also mysterious. It's called Pauli matrices. And the identities is okay. So these are Pauli matrices. And the simple property is that these x, y, z are, say, let me just write down some property. So x, y, z are Hermitian. These are Hermitian. And these are minus I, right? So if you do complex conjugates and transpose, this minus will get I on this position. So Hermitian. And the second thing is that this x squared, y squared, and z squared are both 1. So that means that all the eigenvalue of x, y, z are plus or minus. And the third one is that these Pauli matrices, they are anti-commutes. So xy is minus yx, xz is minus zx, zy is minus yz. So sometimes people will just write x and y are anti-commute. So this is called anti-commutator. But notation is that this AB will just be AB plus BA. Oh, okay. So these are Pauli matrices. And the first property is that this trace of x and the trace of y and the trace of z is 1 plus minus 1, right? 0, 0, 0. Okay. Is it? Okay. And the fifth is that any 2x2 matrices can be written as summation of the Pauli matrices. Because I give you 2 by 2 matrices. There are 4 elements, right? And you can expand these 4 elements into the Pauli matrices. So I give you a matrix, let's say row. I can write as A0 identity plus A1x plus A2y plus A3z. So my question is that how do you get expression of A0? And you can say, oh, I just write down everything and try to compute A0, right? I just solve linear equation. But you don't need to do this. Remember that the trace of these are all 0. So I can take trace both sides. So trace of row will just be A0 times 2. And all these are traceless, right? So A0 is basically trace row divided by 2. Good. How do you get A1? How do I get A1? In terms of trace. Hopefully, let me just write as this, right? So if I have row equals to A0 identity, A1x, A2y plus A3z, I take x times row, then I get A0x plus A1x squared is what? A1 plus A2 xy plus A3xz. So notice that the trace of xy is also 0. And the reason is that probably it's not easy to see, but there's a mysterious that someone, usually the professor will not tell you, but y is actually ixz. I don't know why people seldom talk about this, but you can check. Y is actually ix. Okay. So that means that y is ixz. So this is x squared is 1, so these are 0, right? So let me just, so if you take trace, then you get trace of x row equals to A0 is 0, right? Because x, and you get A1, right? A1, sorry, x squared. X squared is identity. So you get 2 plus all these are 0. So you get A1 equals to trace of row x divided by 2. And similarly, you get A2 is trace of row x, sorry, row y divided by 2. And A3 is trace of row z divided by 2. Okay, so you don't need to do, yeah, basically this is correct. Okay. This is some just small digression, but just tell you that these are the common property of Pauli matrices. Yeah, you can, if you know some the algebra, it's a generator of SU2 or whatever, right? But this is just something that you should know. And why I need to talk about is because now I need to connect these Pauli matrices in terms of bracket. Right, so there's a small example that how do I write this z in terms of bracket notation? I need to write, so z is a matrices, right? But I introduce a bracket notation. So I should able to write z as is a bracket notation, right? So remember, if I use 0, 0 as a, let's say I take v to be 2-dimensional, 0 is just 1, 0, and 1 is 0, 1. So what is 0, 0? This is just 1, 0, 1, 0. So remember this is 2 times, sorry, I'm stupid. This is 1, 0 and 1, 0, right? So this is 2 times 1, 2 times 1 matrices and 1 times 2 matrices. So these are 2 by 2, right? So you should be able to write 1, 1, 1, 0, 0, 0. Good. And I've taken 1, 1, basically it's 0, 1, and 0, 1. And basically 0, 0. So linear, just matrix multiplication, okay? 0 times 0, 0, 0 times 1, 0, 1, 0, and 0, 1. So remember Pauli matrix is, so z is z1, 0, 0, minus 1. So I can write z in terms of this guy and this guy, right? So I can write z as 0, 0, minus 1, 1. Is it good? So this I just try to write z operation Z as a matrix in terms of the bracket notation, in terms of this 0, 1. Okay. So these are just some common notation that okay, so if this is the first time that you see this, you will like feel like very, very difficult. Good. So let me just also write something. So Z is basically 1, 0, 0, -1. Everyone knows about this, right? And the 0 is 1, 0, and the one cat is 0, 1. So the obviously that this 0 is eigenvalue of Z. Z echo on the cat 0 will give you 1, 0, 0, -1, and 1, 0. So you get 1 and a 0. So these are 0. Right, so 0, this cat 0 is basically the eigenvector of Z with eigenvalue +1. Is it good? Hopefully it's trivial, but this is trivial. Now Z1 is 1, 0, 0, -1. You get 0, 1, 0, -1. So it's -1, 0, 1. So it's -1, 1. So 1 is the 1 cat 1 is basically the -1 eigenvector of Z. So why are you talking about this? So now Z is a 2 by 2 matrix, right? And we already find the two eigenstate. So this is why last week I talked about spectral decomposition. Right? So remember, let me just recall a linear algebra, right? If I have like V to V, is Hermitian, this is Hermitian, this is Hermitian, okay? Then I can write T in terms of this lambda J, right? J from 1 to N, and the projector, which is a project to the, see, this lambda J are eigenvalue, right? And the projector is eigenspace. So it's basically VJ dagger, VJ dagger, VJ. Sorry, it's basically this. So if I use this theorem, then I can write Z, right? So this is a linear algebra. Now I need to translate this linear algebra to bracket notation. So VJ here is basically cat 0, and the cat 0 is dagger, right? So it's basically the outer product. So it's 0, 0 with 1 because it's corresponding to eigenvalue 1. Plus it's corresponding to eigenvalue -1. So it's -1, 1, and 1. Right, so it's 0, 0, -1, 1. This using spectral decomposition is the same as this expression, but I just do it, right? It's the same. So this notation, so this bracket notation is compatible with the previous spectral theorem because you know the eigenvalue and you collect eigenvector. And this is generally true. So this is the same. So let me just write down. So okay, let me just also notice the following. So these are simple example, but we will go to general one. So if you take 0, 0, what's so this is operator, right? This is operator that I already showed is 1, 0, 0, 1. So what's this guy apply on what? Say it's apply on what? So remember, if this is the first time you see this, remember to go back to the matrix one. So 1, 0, 0, 0, and this is 1, 0, 1, right? So it's 0, 1. This is 0, 0. So this is just 0. So hopefully this is not difficult. So this is just some notation that you just, oh, by the way, just that you understand the bracket notation. And okay. So obviously that's 0, 0 econ, right? So 0, 0 econ 1 is basically 0, right? Because 0 and 1 are orthogonal. And this is, and so so now you can see the power of this bracket notation, right? Because I know that if I just using this bracket notation, then this will just be 0. And if I want to use this matrix notation, then I probably need to think a little bit and say, oh, 1, 0, 0, 0, 0, 2, 0. Okay. So this is why this is called projector, right? This is trivial because this spectral theorem tell me that this guy is a projector. So, oh, okay. So let me just quickly review what projector means. Projector. So projector is a linear transformation from, let's say, V to V, which is Hermitian, and also their P square is P. So P square, okay, so P square is P, meaning that if you project, right, you project a vector V into some subspace W, this is called projector, right? So this is project, you project into this. So obviously that if you project again, right, you already project once, you project again, it's the same as original, right? So it's obvious. And we can just check 0 and 0 is a projector. So let me just do this, right? So I will do this for two notation. One is a linear algebra, right? So recall that this guy is basically 1, 0, 0, 0, right? So we can do this. This is 1, 0, 0, 0. Okay, good. And then we can also do it using the bracket notation. So what is this guy square? As you did, right? Just 0, 0, and 0, 0. So whenever you see bra and cats, they combine, become a bracket. So this is 0, 0. So what's a 0, 0 bracket? What is this? So this is the same, right? So this is basically the inner product of 0 and 0. This is 1, right? So it's 0, 0. So this square is this. Okay, so these are the same, right? So if you forget about this bracket notation, then you can go back to the linear algebra and make sure you understand. Okay, so this is just this notation. And there's an idea called the resolution of identity. So let me just write down. So resolution of identity. By the way, this is also come from the spectral decomposition. So what is this? 0, 0 plus 1, 1, right? So remember the z is minus 1, 1, right? Plus. So okay, so the first one is that I can write as a matrix representation. So remember these guys 1, 0, 0, 0, and these guy are 0, 0, 0, 1. So this is identity 1, 0, 0. Okay. And but how do I see this from the bracket notation? Right. So how do I do this how can I see this guy's identity? So let me just write, maybe say A to be 0, 0 plus 1, 1. So if I act on any state psi, so remember any state psi I can write as 0 plus 1, right? As a standard basis. So it's alpha A0 plus B1. So we can do A psi. And if A psi is the same as psi for all psi, then A is the identity, right? So let me just read 0, 0 plus 1, 1. And A0 plus B1. Let me just write yes. So it's 4 terms. It's stupid, but let me just do this, right? So the first term is A0 and 0, 0. So A is a constant, right? So constant is fine, then you can take out, right? So you get A0, 0, 0 plus this term and this term. B 0, 0, 1 plus this A1, 1, 0 plus B 1, 1. Okay. And I says that 0 and 1 are orthogonal, right? So remember 0 is 1, 0, 1 is 0, 1. So 0 and 1 are orthogonal, so these are 0. Okay, so you get A0 and 0, 0 is 1, right? So this is 1, and 1, 1 is 1, right? So for any state psi, A0 plus B1, that A psi will be just A0 plus B1. So for all psi. So for all vector, A act on this vector is the same as original vector, so A is the identity. So the same proof. Okay, so like more generally, so if I take V to be any d-dimensional complex vector space, that now you have bracket notation, this powerful tool that I can write a span of 0, 1, up to d minus 1. Remember, if you don't understand this, you can imagine that 0 is just 1, 0, 0, 0, 0, and the 1 is just 0, 1, da, 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 and the d minus 1 will be just 0, 0, d minus 1. Right? Sometimes, because in this quantum information comes, borrow some idea in computer science. So in computer science, that people use 0 as a starting point. If you write some code, right? Usually the first element of the array will be using 0. It's not 1. So this is why sometimes we usually in this we use 0 and 1. Okay. And this if you take I and I bracket I from 0 to d minus 1, this guy will be the identity, the same thing, the same proof as before, right? Before I just say that 0 and 0, 0, 0 plus 1, 1 is identity. Now it's if you take general I, and obviously they become identity. So this is called a resolution of identity. This is the same thing as the spectral decomposition, because basically it is just this I and I just project. So let me just using word. So whenever you take any state here, then you can imagine that this I side will just take the component of that side to the set. So this will just be identity. If you're like, if you can try to see why this is true, should be simple. Okay, so maybe let me just quickly say why this is true. Okay, so if you take say psi, you can write as I, right? So I from 0 to d minus 1. You can imagine that this is A0, A1 dot AD minus 1. Okay, and what is I psi? So I is basically 0, 0, 1, 0, 0, 0, 0 on I's component, right? So if you do inner product with this guy and this guy, then you just take the I's component. Good, right? So I psi will just be AI, because this is just AI. Good. So if you summation of I from 0 to d minus 1, I from 0 to d minus 1, same state psi. That's this guy. By the way, there's no metric here, right? Everything just bracket, just understand definition, write down bracket notation. So I just I do this stupid example just to make sure that you understand bracket notation, because bracket notation is somehow like convenient in the future. Right? If you know some quantum optics or like continuous, that people always use this, because remember in quantum mechanics that people will use this X and P or do something kind of thing. But the infinite dimensional, everything looks trivial. This is okay. And the more that, yeah. So basically, you take any vectors, you take the the d-dimensional vector space, and you take any orthonormal basis. Let's say you take V1, D to be arbitrary orthonormal basis. Now, since you have bracket notation, right? So you can use this. And you can also write identity in terms of this VI and the VI. So this is exactly the same thing. Okay, so hopefully you this is some simple example that you understand. Okay, good. Now let's do some so let me just give you some like also some example of this bracket notation. So we talk about Z, right? We talk about Z. We know that Z0 is 0 and Z1 is 1. What about eigenbasis of X? So X is 0, 1, 1, 0, right? So let me just 0, 0 is 1, 0, and 1 is 0, 1. So what about X on 0? Trivial, right? So 0, 1, 1, 0, just do some computation, 0, 1, 0. So this is 0, 0, 1, 1, 0, 0. And this is 1, right? So this is 1. So X will just flip 0 to 1. Is it symbol x will flip 0 to 1? And obviously, if you do x in 1, then you don't need to do anything again. You don't need to do computation because you know that x1 can return as x0, right? So x0. And we already know x squared is 1 by definition. X squared is 1, so this is 0. So x will just flip the 0 and 1. So x is flip 0. So if you forget about the Pauli matrix x, then you just say that x is some guy which you can flip. So this is called bit flip. So x is called bit flip operation. So bit flip. And if you are from the E department, this is just not. Right. So there's a I forget it. Yeah. So this is also called NOT gate, right? If you are doing like some electrical engineering, right? You start with bit 0, then you take another gate become 1, and 1 becomes 0, right? If you are doing like most, then you just take something like this. This is the high voltage, and this is will be low. If you don't know about this, fine. Right? So this is called NOT gate. Okay, so what's the eigenbasis? What's the eigenvector of x? Right. So notice that this is not 0 is not an eigenvector, right? Because x on 0 will not be 0, it become 1, right? And 1 is not eigenvector of x because x on 1 is 0. It's not 1, right? So what's about eigenvector of x? So let me just tell you the answer, and then we just do some simple verify, right? So so this is a convention. People use plus states. By the way, this is a convention. So plus state is called 1 over square root of 2, 0 plus 1. Oh, by the way, I have not talked about this, but yeah, okay, I will talk about it later. So let's call plus is basically 0 plus 1 up to the normalization. Okay. And then one can define minus is basically 1 over square root of 2 and 0 minus 1. Okay, so what's x echelon plus? It will be 1 over square root of 2, x0 plus x1. So remember that I say 0 and 1, they can flip, right? So x will flip 0 to 1, and this x1 will be 0. But it's the same, right? Plus, right? So it's commutative, so it's 0 plus 1. So this is plus. So x echelon plus will be the plus. So this plus state is basically also called the diagonal basis. So plus is the eigenvector of x. Simple enough. Okay. And how about minus? So you get 1 square root of 2, x0 minus x1. Oh, this is 1, right? This is 0. So there is 1 minus 0. So there is a minus, extra minus sign. So minus 1 minus. So plus and minus, they are the same as x. They are eigenvector of x. Plus is for the plus 1, minus is for the minus 1. Okay, so these are convention. So there are 4 common states that this is 0 and 1, and also the plus and minus 1. So plus state is eigenvector of x and eigenvector of minus 1. Okay, for minus 1 is minus 1. Okay, and we can also check for orthogonality relation. So from the spectral decomposition, then I know that I should be right. Okay, so I can write x in terms of plus. So this is a state, this is a projector, right? Minus plus, right? Minus the eigenvector, the minus 1. So this should be true. This should be true, right? By definition, spectral decomposition, because plus corresponding to eigenvalue 1, minus 1 states, this minus states corresponding to eigenvalue minus 1. And it's a simple exercise. So let me just quickly do why this is true. Okay. To just check by spectral decomposition, we already know this must be true. So just a stupid check. So plus So let me just go back, right? So plus is 0 plus 1. If I written as a matrices, then I just write 1 square root of 2, 1, 1, right? Because plus is 1, 0, 1 is 0, 1. And then this is 1 over square root of 2, 1 minus 1. Here. Good, good. If you have any question, then you can ask. Okay, so let me just do this. So plus is 1 over square root of 2, 1, 1, and the minus 1 is 1 over square root of 2, 1 minus 1. So let's do plus is 1 over, so there's a half, right? Because square root of 2 is square root of 2. So you get 1, 1, 1, 1, minus half, 1 minus 1, 1 minus 1. Okay, so it's half of 1, 1, 1, 1, right? Minus half of 1 minus 1 minus 1, 1. So half, right? 0, half, negative half, right? So it's right? So this is x. So now I do again a spectral theorem and do eigenvector, do eigenvalue decomposition. It's exactly the same. And hopefully this is the good for the bracket notation. Okay. Now okay, so now we have already talked about this x, y, z and identity. And I use bracket notation so that you know the what's the qubit, right? So the qubit definition is just two-dimensional, very simple, just a span of this 0 and 1. And there are, so 0 and 1 is a basis using for z, and you can also do another basis, as I just said, plus and minus. So plus and minus 1 is for, this is for x, and this is for z. Okay, and now let me introduce another operation. This is famous, and it's called Hadamard gate. This guy play important role in quantum computing. So I need to talk about this. So usually called H. So the property of H is, oh, by the way. So remember that we are doing linear algebra, right? So in order to define a linear operation, then I just take a basis of V and tell you that what's it sends to. Then I define H, right? So if I write H in terms of matrices, then basically just this, 1, 1, 1 minus 1. So this means, okay, so it's hard to remember this, right? Probably it's hard, but hard for someone, right? But the property of H is that try to like change to this standard basis. This is called standard basis. This is called diagonal basis. You try to like map this 0 to yeah. So let's do H econ 0. So 1 over square root of 2, 1, 1, 1 minus 1, and 1, 0. It's basically 1 over square root of 2, 1 and 1. So this H will try to map the standard basis to a diagonal basis. So it's plus. Good. And obviously the H econ 1 will be just 0, 1. Then the same thing that you can able to let me okay, so let me check. Sorry. Right, 1 minus 1. So it's this. And the property, okay, so let me just write down. Sorry, you have this H econ 0 is plus, and H on equals 1 is minus. And conversely, so if what's about H econ plus? So let me just write it. 1, 1, 1, 1 minus 1. Remember plus, right? Plus in terms is 1 over square root of 2, 0 plus 1. So you get 1 over square root of 2 is 1, 1. So this is plus. And then there's a half, and you get 1, 1, 1 minus 1, 1, 1. which is 1/2 is 2 and 0. So it's 1, 0, which is 0. So this h on plus states will go back to 0. Okay. And easy to check that h minus 1 will go back to 1. So simply speaking, that this h will try to map the standard base, the eigenbasis of z as a 0, 1 in terms of eigenbasis of x plus or minus, and convert and change from 0 to 1 and 1 to -1. And so easy to check that so h on 0 is plus and h plus is 0, so h squared is 1. So h is a Hermitian operator, and yeah. Okay, so good. Okay, good, nice. So now we have some common gates. One is, yeah, because we are doing quantum computation, so we will talk about. So these are common gates. One is Hadamard, and X and Y are Z and identity. Okay. So this is so-called single qubit. Single qubit. But we will talk about how about the 2 qubits? So in 2 qubits, we can imagine that there are like c squared, and we do a tensor, right? So you will isomorphic to some c to the fourth, as we just said. Okay. So so now it becomes, so usually in 2 qubits, then there are 2 ways, right? One standard notation is we just use writing a span of 0 and 1 and 2 and 3. Right? So it's just notation 0, 1, but since we are in quantum computation, we are starting from single qubit, right? So this 4-dimensional vector space, I imagine that it should compose with 2 single qubit. So I should view as a tensor, right? I should view as a span of 2 small qubits. So one is a 0, 1 vector space, tensor with another. And I just say that by definition of tensor product, every element in the tensor product should be written as a summation of the small bases from V and W by 2. So this is basically written as span of 0 tensor with 0. So 0 tensor with 0, and a 0 tensor with 1, 1 tensor with 0, and 1 tensor with 1. So this is the same, right? If someone writes 0, 1, 2, 3, it's just his notation. But if I imagine that these 4-dimensional spaces come from 2 tensor product, then I can use 0, 0, 0, 1, 1, 0, 1, 1 as a basis. And sometimes that people are lazy, right? So some people will just write 0, 0, 0, 1, 1, 0, 1, 1. And if you really read these 4 bases, and you will see that it's basically 0, 0 will be corresponding to 0, and the 0, 1 will be 1, and the 1, 0 will be 2, 1, 1 will be 3. So what's the relation? This is the binary representation, right? If you write 2 as a binary representation, it's 1, 0. And if you write 3 as a binary representation, it's 1, 1. Is it obvious? Binary representation is basically, yeah, so given any number x greater or equal to 1 is integer, it's actually you can write it as a binary representation. Binary representation just tell you that you can write j to j plus j minus 1 to j minus 1 up to 0, and it should be r belongs to 0 and this is unique. And sometimes people just using bj minus 1 up to 0, which is called binary representation of x. Right, so this stupid is that 0 just be 0, 1. So this is binary. If 0 is 1 is just 0, 1, but 2 It's just one zero, right? Because one means that two times one plus zero. Three is just one. Four is just 1 0 0, right? Because this is power of two. The power of two is basically highest. So five is 1 0 1. 6 is just 1. Should be like this is, and it's basically unique. Yeah, there are some like interesting like brain teaser interview questions about this. Yeah, this is called the binary representation, right? So obviously there's three is called 1 1, right? So it's exactly the same. Okay, good. Hopefully this is obviously for someone, for you guys. Okay, so if now it's mystery. It's not there's not nothing uh amazing, right? If you start with 3 qubits. Oh, by the way, so sometimes that people will be lazy, right? So if I take 3 qubits, then it should be a dimension, right? Because 2 times 2, 2 times 2, 2 times 2 times 2. So someone will just write tensor 3, just for, and then this is isomorphic to C8. And it's the same as that if you use the standard one that you can write CA as 0, 1 up to 7. Right, but the more common notation is that I view as a tensor product with 3 small plus base. So it's span of 0, 1, cube. So it's 0. So there are 8 bases. One is 0, 0, 0. Sorry, sometimes so people are lazy, right? I just write 0, 0, 0. I mean, so this you should view this as 0, tensor 0, tensor 0. And then 0, 0, 1, and 0, 1, 0. Yeah, 0, 1, 1, and 1, 0, 0, 1, 0, 1. And then it's corresponding to 0 as a binary representation. This is 1, 2, 3, 4. Right. It's the same. 4, 5, 6, 8, 7. Okay. So this is a common. This is just notation. Is it understandable? Okay. So the question, stupid question. How do I produce if I take two, let's say I have n qubit, right? So I can now generalize. I have a 2 qubit, sorry, I have one system with single qubit, now I have n qubit. So I can say that C2 tensor with n. So which is a vector space with complex of 2 to the n dimension. This is the same. Quantum mechanics tell you that yeah, basically there are exponential amplitudes. So any states inside this need to use a 2 to the n complex number to write C, right? So it's exponential. And if you learn some computer science, that people hate exponential, right? They try to find some like polynomial algorithm. So write down all the complex number is difficult. But now the question I want to ask is simple. How do I generate these states? So how do I generate the states, which is a linear combination? So I want to write X. Okay, so this is notation that I will keep, the textbook will keep use. So I write X into 2 to the n minus 1. How do I generate this state? So this state is written as 0. So there are 2 ways to write this, but now I'm using binary representation. So every number from 0 to 2 and 2 to the minus 1, I can represent as binary, right? So basically what I'm saying is that this is just 0 plus 1 plus 2 plus up to 2 to the n minus 1. And I can write everything in terms of binary. So the question is that how do I generate this state? Obviously that I need to take like 1 over 2 to the n to make sure that these states are normalized, normal. How do I generate this? How do I start with? Yeah. So let me just maybe do a simple example. So so let's take n equals to 2. So I want to have a state, right, written as an order superposition of this. And I can write as a binary, right? So 0, 0 plus 0, 1, 1, 0 plus 1, 1. So this is not anything special. I just write 3 as a binary representation, and I spread into 2 qubits. Now I can write as a 0 plus 1 tensor. Remember that this is tensor 1, 0, 0 plus 1. Obvious, right? 0, 0, 1, 1, 0, 1, 1. And this is Hadamard gates econ 0, right? You remember that Hadamard econ gates will give you plus, right? This is plus states. This is plus state. And up to like this is if you take 1 over 2, 1 over 2, 1 over 2, then you become this. So this is H econ 0, tensor H econ 0. And this is plus plus. So sometimes people are so lazy. So we will write as H squared. So remember H squared H tensor squared, meaning that the first H, first Hadamard gate econ 0 cube, the first qubit, second Hadamard gate econ second qubit as a 0, 0. So H econs twice on 0, 0 states will give you all the linear superposition from 0 to 3. Basically, it's all the linear, all the linear sum. So H tensor square 0, 0 will give you 1 over half of summation x. I written as x 0 to 3. Okay, so now I need to change back to binary. I always, so basically this kind of notation is basically I need to always like translate the binary representation to the number basis, but just okay. And if I do cube, let's say I cube on 0, 0, 0, then I get 0 twice cube. So I get plus tensor. Sometimes someone will just write plus. So this will be 1 over 2 square root of 2, 0 plus 1, 0 plus 1, 0 plus 1. So there are 8 of them, right? But if you write a binary representation, that basically you are doing 0, 0, 0. So you have 1 over square root of 2, 0, 0, 0 plus 0, 0, 1. And you get this, you get exactly this for the standard expression. 1, 0, 1, 0, 1, 1, 1, 1. So they are all different. And if you written as a binary representation is 0, 1, 2, 3, 4, 5, 6, 7. So that means that this guy is the same as summation of x from 0 to 7, 1 over square root of 2. Is it? Simple. So there's no mystery here. The mystery is that we try to use a binary representation to the tensor product and translate back to. So this will give us a simple expression on Hadamard gates econ all the 0 qubits. So by the naive proof that H tensor n on 0, 0, 0, 0, there are n of them, will be written as 1 over 2 to the n summation x about the square root of 2 from 0 to n minus 1. Okay. So square root of 2, just make sure that it's normalizable. Okay. Good. Okay, so this is a property of Hadamard gate. N-dimensional Hadamard gate. X on n qubits. Okay. But let me just, what's the time? Okay. So I think, okay. So these are just common properties. Okay, so I want to talk about some other stuff, but the time is limited. So let me just also do some review of this bracket notation. So how to write trace in terms of bracket, notation. Right, so remember, everyone knows about trace, right? So given a trace of matrices will just be the sum over all the matrix diagonal elements, and also the sum of the eigenvalue. Hopefully, this is everyone knows about this, right? And obviously that is trace of xy is always a trace of yx. So notice that this is only cyclic once, right? So the trace ABC is different from trace of ACB, right? Hopefully you notice. Because this equation can only implies that this guy is the same as trace of CAB, and also trace of BCA, right? So these three are the same, and then there will be another three. So the trace of CBA and the trace of BAC. So the trace can only commute two of the two guy, right? If you try to use three guy, then it's not sure that they are the same. Because you can only, yeah, it's is it obvious? So this is true, right? But start from here, then you cannot prove. It's obvious that this is not the same. Because whenever you use it, you can only, if you want to use this relation on this, then you need to combine BC. So you can only prove that trace of ABC is the same as BCA. And then trace of CA. So you always get some even permutation. And for this, you always get odd permutation. So these two actually are not just some common like knowledge about trace. Because because someone I remember that someone said this is true, but actually it's not. Okay. Right. So how do I write? So this is a relation. Okay. So this is the trace. How do I write? How do I write trace in terms of some like how do I write trace in terms of this so-called bracket notation? So remember in quantum mechanics, right? In quantum mechanics that you learn about so-called expectation value. So let me just quickly say something. This is not important, but so you know that this is expectation value, right? So expectation value is that I give you Hermitian matrices, and for state psi, and the expectation value by definition will be just written as this. So so now I use bracket notation, very like smoothly. I say so basically this just means that the state psi acts on the A. So this is a cat vector, right? Inner product with another guy. So this is the expectation value. This is the inner product with psi and this guy. So this is a number. It's a scalar, right? It's a scalar. And since A is Hermitian, so this guy must be real. It's actually real. So this is why in the experiments that we can measure, right? Okay. So so this is the so-called measurement results. If I give you a state psi and you tell me that you want to measure A, the expectation value of A will just be this. And it's just a check that one can write this as a trace. So actually I can write this is trivial, but A size. Actually, okay. Why this is true? Because that I say so this is a mysterious part of bracket notation. Remember that I say that trace of xy is the same as yx, right? So the trace of a on state cat is psi. You can just change change the direction, you can just exchange this too. So you get this. Right? But this guy's a number, right? So take trace is not important. And it's easy exercise for you to check that this is true. To check that if you don't use this, then you can write down the definition of the cat and do this. Okay, and I think this is what. Oh, finally, let me just say some final words. So next time that we will talk about so-called Bell inequality. So I want to talk about this phenomenon. So this is a trivial fact, but it's the main thing. So if I take two qubits, right? Let's say V tensor V, C square, I take two qubit. Then I say there is a state. This is called Bell state. It's called Bell. It's 0, 0 plus 1, 1. And then take a square root of 2. And hopefully you are familiar, you are like now much familiar with this bracket notation. So 0, 0 meaning that this 0 tensor 0, and the 1, 1 is 1 tensor 1. So there are like two qubits. They are far apart, and there are states which looks entangled, but looks as this. So one thing I want to say is that these states cannot be written as the one state on the left-hand side tensor product with another. So these states cannot be written as alpha 0 plus beta 1 tensor, let's say gamma 0 plus delta 1. So right, this is an interesting question. Is that all states is basically because we are doing tensor product, right? So I'm claiming that this Bell state cannot be written as one state from the left and another state from the right. And the proof is simple. You just write down, you get alpha gamma 0, 0 plus alpha delta 0, 1 plus beta gamma 1, 0 plus beta delta 1, 1. Right? So in order for these states to be the same as 1 over square root of 0, 0 plus 1, 1, then you immediately must have the cross term to be 0. Because 0, 1 and 1, 0 are different bases, right? They are also normal. So alpha delta must be 0, and also beta gamma to be 0. But if alpha delta is 0, that means that alpha is 0 or delta is 0. And also beta is 0 or gamma is 0. And obviously this cannot be true, right? If alpha is 0, then there's no 0, 0 term. So alpha cannot be 0. But if delta is 0, then there's no 1, 1 term. So the contradiction. Because I try to solve this, but there's no solution. So I cannot write the original Bell state in terms of two product one. Product from the left and product from the right. So next, yeah. So this is the property. Okay. And I also do some. Let me just do some simple calculation so that you understand this. Okay, so this is property. This is the common property of. This is trivial property of Bell state, right? So what I want to say is that these Bell states can also be written as, if you change the basis, can also be written as plus 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 minus minus square root of 2. Now everything become like weird, right? So why this is true? So remember that this guy is basically 1 over square root of 2, 1, 1, and the minus 1 is 1 minus 1, 1 over square root of 2. So we just check this. So this is an easy exercise that we just check. So half, maybe let me just write. So plus is basically square root of 2, 0 plus 1, 1 over square root of 2, 0 plus 1. plus is equal to half of 0 minus 1, and then 0 minus 1. Okay, so let me just do this, and you get 1 over square root 2, half of 0, 0 plus 0, 1, 1, 0 plus 1, 1 plus 0, 0 minus 0, 1 minus 1, 0 plus 1, 1, right? So this of diagonal term cancel, and it becomes the same thing. Half of 2, 0, 0, half of 1, 1. So we prove these results. Okay, so this is one property of this Bell state. Basically, you can imagine that this Bell state. Basically, this state is also called a Schrödinger state. So you can imagine that these states either one could be is from 0 to 0. And now, guys, so there are non-trivial correlation between the first and two bits. They have to be the same, but they have to be the same as. If you change the basis, they still need to be the same. So either you go 0, 0, 1, or either you can imagine that this is plus, plus, or minus, plus. So this means that any state, this tensor product factorization is not unique, right? So any state, if you write one state in terms of tensor products, the decomposition is not unique. You can also change the basis and get different decomposition. But Bell states give exactly the same message. Okay, so yeah, I think this is for today. Okay. Next, so tomorrow we will talk about some measurement and yeah, that's it. 大概是这样。Yeah, that's it. Oh, by the way, and I will try to like upload the PowerPoint every week. And I also have records, so yeah, if you forget about this, you can just read. Yeah.